Hello everyone, I'm Nandini Vemuganti and today I'll present mobile door detection for accessibility, how AI and computer vision can support independent navigation for visually impaired users. Firstly, we'll discuss the navigation challenges faced by 285 million visually impaired people. Then we'll look at our target users, sensor and AI approaches, current challenges and future directions. The problem? Doors are essential landmarks for safe mobility, yet remain one of the hardest objects to detect. Without visual cues, people impaired struggle with entrances, exits, and spatial orientations in daily life. Our target audience are our solution benefits three groups: blind and low vision individuals, seniors and mobility aid users, and even delivery robots that require autonomous navigation. Like you can see in the table, we have different types of sensors like RGB cameras, which are affordable but are less reliable in low light. Depth cameras offer better 3D awareness. The other ones gives highest accuracy but is not affordable, it's expensive, while IMUs are power efficient but less accurate. Combining RGB and depth cameras gives the best balance as of now. Coming to classical vision methods, earlier techniques like edge detection, line transforms, and texture analysis worked in simple settings but struggled with lighting changes, clutter, and complex environments. Like you can see, first we need to process the image, then we need to have the edge detection, then we need to even analyze the shape of the door. So, coming to deep learning revolution, deep learning raised accuracy about from 75% to 95%. YOLO, in particular, enabled real-time detection at 30 plus frames per second on mobile devices, making navigation assistance practical. Like you can see here, there are in the graph, I have differentiated the accuracy for each of the method. YOLO has 92, Transformer has 94, whereas multimodal has the highest 96. These methods, as of now, they are varied. They are affected by the surroundings of the door of the methods that they are text like that they are tested. Sometimes the accuracy drops around 10% depending on the surroundings. Like we mentioned, unlike traditional two-stage detectors, YOLO performs object localization and classification in a single forward pass, significantly reducing computational overhead while maintaining high accuracy for door detection tasks. Lightweight models like MobileNet, Efficient Det, and YOLO V5, YOLO V8, that are different versions of YOLO, achieve high accuracy, fast inference, and low power consumption, making them well suited for smartphones. While we talk about success and failures, these systems work best in well lit conditions with clear door frames. Failures occur with glass doors, occlusions, poor lighting, or motion blur. For example, glass doors, they are hardly detected because they are very transparent. Very few are detected, that too because of the reflections that occur on the glass doors. We also have other occlusions to solve, like if the door is opened or closed, or if it is locked, even if it is opened in a particular angle. So these are occlusions that people has difficulty in facing. So one uh, one success is successful integration with voice feedback for accessibility applications. Uh, we also have, you know, reliable detection of office doors, hotel rooms, and standard entrances. So every building is different as of now. So hospitals have the dim lighting, the other offices, residential areas are bright. So most of the methods which we follow, they change, the accuracy change according to the surroundings. Challenges include supporting many door types, maintaining real-time performance under power limits, and generalizing across diverse cultural and architectural designs. The We have models must work across diverse architectural styles, cross domain adaptation. We also need efficient inference with limited computational resources. So it also depends upon the devices which we use. They need to be transparent and reflective surface detection, partial occlusion, and crowded environment also changes. So coming to the future directions and innovations, the future lies in vision language models for natural interaction, multimodal sensor fusion for robustness, and edge AI optimization for speed and efficiency. Vision language models, also known as VLMs like GPT-4V and CLIP, enable natural language interaction with door detection systems. Users can ask complex questions about the accessibility or the door status. They can also ask, like, if a physical impaired person can ask, is this door wheelchair accessible, or how do I open this glass door? So the VLMs provide contextual and helpful responses. So, key takeaways and implementations from this research is, to succeed, systems must achieve 90% plus accuracy. Also, they should have latency less than 50, and multiple feedback modes should be implemented. Like, they should do a lot of tests on the different kinds of data sets, and also seamless integration with accessibility frameworks is also one takeaway that should be implemented. Key data sets include open images and other subsets. Important papers from ICRA and CVPR, and open source code available on GitHub. Thank you. Uh, Before ending the presentation, I would also like to give you an overlook of the website. So this is the website that I have designed. It has the audio tutorial too, combining so that it can be accessed by everyone. I have different web pages. One for the problem. Here is the audio. You can listen to it instead of reading it, so that it can be accessible by everyone. The sensors, it covers everything, classical methods that we have covered in the presentation. So it covers everything in detail, like learning methods. We have deep learning revolution, object detection frameworks, two-stage detectors, one-stage detectors. We also talked about YOLO. I have inserted few images here and there. mobile optimized architectures. We talked about MobileNet SSD, its efficiency compared to efficient Deadlight. Training a data set, how training a data set is required. We need more data of the doors, or what kind of doors, multiple hallways that are used, so that we can have accurate solutions. So here's the difference between on-device versus cloud inference. This web page showcases successes and failures. We also have challenges, the future implementation. We talked about VLMs, transformer-based architectures. Here are few references that I referred, and also the current lab work. Current researchers are working on this project. So here's an interactive quiz. Uh, you can answer, will YOLO V8 nano model detect this door successfully? It does, because it has 90% accuracy, more than 90%. It's correct. We also have a question for Glassdoor. What is the main challenge for detecting this door? Weak edges, transparency makes it nearly invisible. We can partially occluded door. How we can improve detection of partially occluded doors? Maybe, yep. So, what feature would be best distinguish this window from a door? Color of the frame. It's wrong. So we have multiple questions. Once you have done the tutorial, you should be able to answer these questions. You can hear the tutorial. So I also implemented easy access through the web page. You can access the pages from here or also from here. This is the big bibliography. These are the papers that I referred to. So these are the papers that are less than 5 years old. They are mostly from 2022 between 2024. So that's all about the door detection tutorial. Thank you, everyone.